So welcome to Friday's lesson, and what I'd like you to do for today's lesson is to listen to my explanations and stop when I say stop and carry out the exercise that I recommend. I know it would be very, very tempting to just watch the whole thing straight through, but that's cheating. I'm going to try and keep the entire lesson to no more than a double period, which is what we would have in class today. Fingers crossed that this can happen. So what am I going to do in this video? Well, firstly, I'm going to review uncertainties first, what the different types of uncertainty. I'm going to review addition and subtraction of quantities. Now, what does that mean? Well, when you have two quantities, as in like finding the perimeter of a square or a rectangle, you have A and B. What happens if you have to find that perimeter? And what would the consequence be on the uncertainty, the absolute uncertainty? Then we're going to look at multiplying a quantity by a constant. So let's say you were working out the perimeter of that square. That looks like a rectangle, but it should be a square. And you have four sides B that are exactly the same. You could do B plus B plus B plus B, or you could just do 4b. What is the consequence of that 4 on the absolute uncertainty? The next thing we're going to do is look at multiplying and dividing quantities, which is the most common exercise that you'll be doing. So when we're trying to work out things like force equals mass times acceleration, or work equals force times distance, this is what we mean by multiplying quantities. What is the absolute uncertainty in your values of F and work? How do we calculate those? And then right at the end, we will work out quantities to a power. For example, when you're working out the area of a circle, which is pi r squared. What is the uncertainty in our area? How do we work that out? So those are the 5 things we're going to be looking at now. I definitely recommend that you take some notes as we go, and I'll say it again. Please stop to carry out the exercises when I say. Today's interruptions will be brought to you by cats and probably a fair amount of rain, possibly even thunder. So let's review uncertainty so far. There are 3 types of uncertainty. We have absolute uncertainty, fractional uncertainty, and percentage uncertainty. The absolute uncertainty is the uncertainty that's expressed as a result of the actual measurement from the instrument. So A plus delta change in A could be a measurement of distance, right? So you could have, for example, 4 meters plus or minus, there should be a minus there, 0.1 meters. I've never actually gone over this, but the unit goes at the end. You don't have to write it twice. So this is what we mean by the absolute uncertainty. The reading that we've taken from the instrument, which, depending on whether it's digital or analog, will be more or less precise. The next one is the fractional uncertainty, and that's when we write the absolute uncertainty as a ratio of the actual measurement. So in this case, it would be correctly expressed as delta A over A, which in the case of our example would be 0.1 over 4. That's our fractional uncertainty. The next would be percentage, and that happens to be the fractional expressed as a percentage. So it's exactly the same as the fractional in effect, but this time we are multiplying that fraction by times 100. Okay? If you work that out, it should give you 2.5%. which is equivalent to our fractional before. So it really depends on the question. If you feel that you need a little bit of practice now, work out the percentage uncertainties for these values. If you think you've got this, then you can go straight on to part 2. So work out the percentage uncertainties for these 3 if you feel that you need to practice. Okay, here are your solutions, if you can check them. We have 0.1 over 6 for this force, which should give you a percentage uncertainty of 0.17. The next one, which is a distance, 3.4 plus or minus 0.1, should give you a percentage uncertainty of 3. And then 42.341 plus or minus 0.05 seconds this time should give you an uncertainty of 0.12%. Okay, so if you've got this, you're ready to move on. So here we're doing reviewing the addition and subtraction of quantities and what happens to the absolute uncertainty of the final quantity at the end, right? So let's take an example like a triangle. Let's take a triangle that's all over the place like this one. Okay, you have a distance A, B and C, and I need to work out for some reason the total perimeter of that triangle. Okay, so the formula, what I need to do first is to actually work out the perimeter. So let's use some distances first. And here are 3 distances that I've just completely made up. I don't know if they're mathematically sound, and I don't care, quite frankly, because what we're focusing on right now is the uncertainty. So what do I mean by the absolute uncertainty of the final result? Well, I first need to work out the actual perimeter. That is the fundamental thing, the most important thing, right? So my perimeter, my total distance that I need to cover if I go around that triangle is going to be A plus B plus C. So that answer would then be 19 meters, and I hope you can see why. 10 plus 4 plus 5. Okay, so you've got 19 meters. So that's my final answer. Bang. So if I had to plant a bed of flowers all the way along, then I can now work out how many flowers I need. However, what I need to know is my range of uncertainty, because I guess if I'm going to fill the perimeter with flowers, I need to know just in case how many extra ones to buy, right? There has to be a little range of uncertainty. So what I need to do now is to apply the rule, and the rule for addition and subtraction of quantities is that you add the absolute uncertainty. And you would express that like this. You would add the uncertainty in A, the absolute uncertainty in A, to the absolute uncertainty in B, to the absolute uncertainty in C. So that would be 1, which is the uncertainty in A, plus the uncertainty in B, plus the uncertainty in C, which gives us a total uncertainty of 3 meters. So our final answer then would be 19 plus or minus 3 meters. How could that be in any way useful? Well, if you're planting, say for example, a flower every half meter, then I will know that I'll need to bring 6 extra flowers just in case. Okay, does that put I'm hoping that will put the uncertainty in some bit of a practical context. Okay, so that's addition and subtraction. And again, it doesn't matter if you're adding or if you're subtracting. It's exactly the same thing. Okay, so I'm now going to give you some examples to try. If you feel that you are really confident with this section, you may fast forward to the next one, number 3. Okay, if you need the practice, try this one. Find the area of the following shapes. We have a triangle A, B and C, and a weird quadrilateral thingy which has sides A, B, C, and D. So find the perimeter of all of those. I've written area and I did not mean area, I meant the perimeter. So please excuse that. Okay, the uncertainties are here. So you've got A is a distance of 4 plus or minus 0.1 meters. B is 8 plus or minus 0.2 meters. C is 6 plus or minus 0.1 meters. And D is 4.5 plus or minus 1 meter. Okay, so give it a go. Stop the video now and try working out the perimeter of all those. Okay, so the first step is to actually find the answer. What is the perimeter of these two shapes? So the first one would be A plus B plus C. So adding up these three distances, 4 plus 8 plus 6, would give you 18 meters. And then the second part, actually find the answer, the perimeter of the weird quadrilateral thing, and you would get 22.5 meters, which is 4 plus 8 plus 6 plus 4.5. So that's your first step. Now we're going to find the absolute uncertainty, and we have to apply the rule. And the rule is actually delta A plus delta B plus delta C, and then for the second part you would add delta D, but this is for the quadrilateral. Okay, so let's work that out. And then for the absolute uncertainty in the triangle, we would have 0.1, which is this uncertainty, 0.2, which is this uncertainty, 0.1 again, which is the uncertainty of C, and that would give us an uncertainty of 0.4 meters. So that would be the answer for the triangle is 18 meters plus or minus 0.4 meters. We could just cross that meter out and leave it on the outside, okay? So 18 plus or minus 0.4 meters. For the trapezium or quadrilateral, we would now add 0.1 plus, which is the uncertainty in A, 0.2, which is the uncertainty in B, 0.1, which is the uncertainty in C, and 1, which is huge, which is the uncertainty in D. And that would give us an uncertainty, an absolute uncertainty of 1.4. So now our answer is 22.5 plus or minus 1.4 meters. Now if you hear something strange in the distance, it's the heavy breathing of a rather overweight cat sitting very close to the iPad. It's not me. Okay, so now we have our answer. We can move on to what happens when you multiply a quantity by a constant. Right, number 3. So how do we multiply a quantity by a constant? Or rather, what I mean is, what happens to the absolute uncertainty of a quantity when we multiply it by a constant? I'd like to think that you all know how to multiply a quantity by a constant, but what happens to its uncertainty? And what that sort of looks like is, well, if you have a quantity x and you multiply it by a constant, that constant could be 4. It could be some kind of scientific constant or mathematical constant. It could be pi x. It could be acceleration due to gravity. It's any constant which does not involve any other variable. Okay, so you do come across a lot of those in physics. And basically, it's very straightforward. Let's take the first as an example. 4x is actually another way of writing the following. X plus x plus x plus x. So 4 times a quantity is actually equal to the addition of that quantity by itself by the number of times stated in the constant. So what we're doing is we are adding a quantity, in effect. Now, what does that mean in terms of uncertainty? See if you can figure it out. What do you think the rule is for multiplying a quantity by a constant? Have a go, have a guess. Stop the video. Well, in order to find the total uncertainty in this situation, what you would do is, assuming, of course, that the uncertainty in x is delta x. That's what we're going to take as our uncertainty. Then the rule is that you add the uncertainties, the absolute uncertainties of each quantity. So in this case, you would add delta x plus delta x plus delta x plus delta x. Now the way to tidy that up now would be to just write 4 times delta x. And what have we got there? I've seen that 4 before. Here it is. It's the constant, isn't it? So basically we have a rule there, a much, much easier to apply rule. When you are multiplying a quantity by a constant, you multiply the absolute uncertainty by the constant as well. So if now we need to work out pi x, and x has an uncertainty of delta x, right, then the final answer would be pi x plus or minus pi delta x. Okay, let's give it a go. Let's try a few examples. It's not too painful. Right, so try the following questions. The first one you're going to do is to work out the circumference. So work out the uncertainty, the absolute uncertainty in the value of circumference for this circle, this one here, when the radius is 3 plus or minus 0.1 centimeters. And then I also want you to work out the perimeter, full perimeter of this triangle, this square. Considering that it's a square, so the perimeter will be equal to 4 times a. 1, 2, 3, 4. They're the same size, so it's 4a. What is the final absolute uncertainty in the value of the perimeter? Okay, so stop the video, and I mean it, stop it, and work it out first, and then we can check your answers. First step, work out the actual circumference and the actual perimeter. So that's, don't even touch the uncertainties yet. You first have to work out the actual answer, which in the case, okay, so if you just apply the simple formula, circumference, where's my little dot? Circumference equals 2 pi r, where the radius is 3 plus or minus 0.1. You get 18.8 centimeters, and for perimeter, it's just 4 times a, 3, 4. So that gives you 16 centimeters. So that's our answer. Now we need to work out the uncertainty. Now what is our actual rule? The rule is the constant. Alright, so whatever our constant is, in this case it's 2 pi, and in the perimeter case it's 4, times the absolute uncertainty. So for the first one, the circumference, it would be plus or minus 2 pi times 0.1. Okay, so it would be 2 pi times 0.1. So that gives us 2 pi times 0.1, it gives you 0.6. So the final answer to this question would be 18.8 plus or minus 0.6 centimeters. And in the perimeter, we would have 4 plus or minus, our answer is 16 plus or minus 4 times the absolute uncertainty in A, which is 0.1, which gives us 0.4. So the final answer for this one would be 16 plus or minus, that should be 16.0, didn't I do that before? 16 plus or minus 0.4 centimeters. Okay, so I hope you got that right, and we can move on to number 4. Just a note though, if you've been doing every single exercise and practicing everything, you now need to take a bit of a break, 10 minutes, 15-minute break, do something else for a while, because it gets harder now, and if you're already a little bit fatigued, then it's not really going to go in. If you've been skipping bits, then you can go straight into the next section. Okay? Okay, so now let's look at multiplying and dividing quantities and the effect on absolute uncertainty. So now's where it gets a little bit trickier. What happens when we take two quantities like mass times acceleration in order to find force, for example, and we have uncertainties in each of those, like delta mass and delta A? How do we work out the final absolute uncertainty in the force? Now, the best way to deal with this is using fractional uncertainties, right? Because the fractional uncertainty is not the absolute. So now we're going to forget about the absolute uncertainty addition stuff. Before we were adding absolute uncertainties. Now we are going to add fractional uncertainties, because the fractional uncertainty in F is equal to the fractional uncertainty in the mass times the fractional uncertainty in A, in acceleration. Now, if this is a little bit too hard to handle at this stage, and you skipped the previous exercises, you need to go back and do those completely, because if you haven't got a handle on fractional uncertainty, then this is just going to be nonsense, right? If you are struggling with it, but you've done all the exercises, just bear with it and go through them with me, the following examples, and I think we might get there. Okay, so let me give you an example. I'm trying to work out the force on a car. Let's take something really simple and basic. So I'm going to draw a car now very badly. Looks like it's had a few problems and there's something rather 1960s about it. So I don't dislike it completely. Here we have a car, and it has a mass M. Let's make that mass 800 kilograms. Rather light, but anyway, doesn't matter. Mass 800 kilograms, and it has an acceleration of 5 meters per second squared. Okay, now I'm going to add some uncertainties. Now hopefully you're noticing that the whole significant figure, or decimal place in this case, aspect to this, because it's always the smallest possible interval, isn't it? So if this mass has a uncertainty value of let me rub that out, of 1 Newton, okay, or 1 kilogram, sorry. Start again. So this mass, 800, has an uncertainty, using its smallest possible interval, of plus or minus 1 kilograms. Okay? And the acceleration has an uncertainty, if we look at the smallest possible interval, plus or minus 0.1. Okay, ms minus 2, assuming that all of these have been measured with digital instruments. If that doesn't mean anything to you, don't worry, because we're going to stick to just the calculations for now. So look, we have mass, acceleration. Now I want you to work out the force of the engine that's making this mass accelerate by 5 meters per second squared, and then I want you to work out the uncertainty in that value, the absolute uncertainty in that value. So the first step is always to actually give me the answer that I need. I actually want you to tell me what the force is. So the force would be equal to mass times acceleration. So see if you can work that out now. Okay, so hopefully you got a value of 4,000 newtons, right? So that's our answer. And what that is equivalent to is F here, right? So let's have a look at this formula again. What we've got is absolute uncertainty in force over the actual value of force is equal to the absolute uncertainty in m, mass, over the real mass, times absolute uncertainty in a over a, or acceleration. Okay, so now what we're going to do is we're going to substitute all those values into the equation and solve for the absolute uncertainty in F. Try doing that yourselves and see if you get the same answer as me. Now hopefully you got an answer of 85 newtons. And let's have a look at how I got that answer. This is our absolute force, our absolute uncertainty in force, which is what we're looking for. This is our value of F. This is our uncertainty in mass, our uncertainty in acceleration, and our acceleration. And finally, this is our uncertainty in force. Okay, let me give you a couple more to do to practice this concept. Okay, so try this question. I want you to work out the force needed to make this badly drawn lorry accelerate 25 meters per second squared. I should say squared. Okay, so I first want you to work out the force, which is mass times acceleration, needed, and then work out its absolute uncertainty. And then what I want you to do is to work out the amount of work needed to be done to make the badly drawn lorry with what looks like a flat tire move a distance of 6 meters. Okay, and then I want you to work out the absolute uncertainty in the work done. Okay, so the first thing that you have to do is to actually find the value of F and find the value of W. So find me force and find me work. Stop the video. Okay, so hopefully you managed to do this without too much of a problem. First, find out the force using mass times acceleration. If you multiply 1,000, which is the mass, times the acceleration, 25, you should get a value of 25,000. And this is F. Similarly, the work done is force times distance. Force is 25,000 times 6, which I took from up here, the original distance. That gives me a amount of work of 150,000 joules. And that's our work W. Okay, so now let's look at the uncertainties. The rule is that to find the absolute uncertainty in F, the fractional uncertainty in F is equal to the fractional uncertainty in M plus the fractional uncertainty in A. Oops, made a mistake. Let me rewind. That should be an A. So let's put those values in and work out the answer. Okay, so if we substitute the values in, our force is 25,000. Our delta M is 1 over 1,000 for the mass, fractional uncertainty of the mass. Then we have delta A, 0.1 over 25. Okay, and if we add these up, we should get 5 times 10 to the minus 3, which we now need to multiply with 25,000. So 5 times 10 to the minus 3, which is what this is equal to, times 25,000 should give you 125, which is our fractional, is our absolute, scrap that, it's our absolute uncertainty for F. And that would be the answer for F. Now let's apply that answer to work. Okay, so now we have an actual value for work, which is 150,000. So now let's apply the formula to the situation of work, force times distance. But first, let me add an uncertainty because I forgot it. Plus or minus 1 meter here. Okay, so now the force is 25,000 and the distance is 6 meters with an uncertainty of 1 meter. Work out the absolute uncertainty in work. Off you go. And don't forget to stop the video. So substitute the values in. Hopefully you found the easy to identify that was 150,000. That's the work done. That's W. And we have our absolute uncertainty in force over the force, which is 25,000. And then we have delta D, our uncertainty in distance, which is 1 over the distance, which is 6. So now our absolute uncertainty working out includes the following step. Work out the fractional uncertainty in work done, which is equal to this section. Okay, and this should give you approximately 0.17. I want to check that in a minute. And then you multiply by 150,000. And that gives you an absolute uncertainty of 25,000, which is absurd, or it looks absurd. It seems like a ridiculously large amount, 25,000 joules. All right, but it's only actually 17% of the actual value. So 20% uncertainty. It's not great, but it's not terrible. Okay. Anyway, I hope you got that answer and you're confident. And now we're going to move on to the last section, which is a quantity to a power. Right, so what happens to the absolute uncertainty of a quantity when it's to a power, when that quantity is to a power? And I'll explain briefly why it looks the way it does, using an example. Let's say we have, we need to work out A. Come on, my pen's not working. Hang on. A equals B squared. So we have a quantity B plus or minus its uncertainty. There we go. And I want to know what the final absolute uncertainty is in A, which I would express like this. Oops, A. So I'm looking for the absolute uncertainty in A. Right. Now another way of writing exactly the same thing is to write A equals B times B, right? I hope you can tell that A equals B times B is the same as B squared. Now what is the rule in this situation? Hopefully you know this. The rule for absolute uncertainties when you're multiplying is that the fractional uncertainty, you get rid of that, in A would be equal to the fractional uncertainty in B plus the fractional uncertainty in B again. So in effect all we're doing is multiplying the fractional uncertainty in B by 2, which happens to be the power. Now that's not a coincidence, and in fact we could apply this to other examples, further examples. If the power was 3, then you would have an extra fractional component here, and then you would see that this was in fact a 3 as well. So there is a general rule. If we have A quantity to the power n, then the final fractional uncertainty is equal to delta A is equal to, the fractional uncertainty in A is equal to n, the power, times the fractional uncertainty in B. Alright, so that's the general rule. Now let's try an example. Let's say I wanted to work out the area of this square, and the length of one of the sides is equal to 5 centimeters plus or minus 0.1. The area would be b squared. So just quickly work out an area value first. Find out what the actual area is. Now that hasn't been too taxing, I hope. So you should have worked out that b squared, which is 5 squared, is now 25 centimeters. Great. So now let's work out the absolute uncertainty in the area. The rule is as follows. The fractional uncertainty in A is equal to 2, because 2 is the power, okay, squared, times the fractional uncertainty in B. So actually work it out. Have a go. Okay, so first step, our fractional uncertainty in the area is equal to 0.04. So now I'm going to multiply out 0.04 by the actual area, which is 25. Okay, so 0.04 times 25, which equals 1. So our final answer is 25 centimeters plus or minus 1 centimeter. You can get rid of that centimeter there and put it here. Okay? 25 plus or minus 1. Okay, so those are the 5 different types of uncertainty situations that you need to be familiar with. I'm going to give you some more examples to practice, and I'm just going to give you the answers this time. I'm hoping that you can work your way through all of those without too much of a struggle, and I'd rather you finish that than go over the questions on the booklet. Okay, so now try the following situations. They use all the formulas that we've applied, and I think you'll be fine. Just remember that for this one, x, y to the half, I'm going to write this one here, x, y to the a half. Okay, have a go at these. These might get a little bit tricky later, but I think definitely up to here, you should be able to do them with no problems. These two are a bit of an extension. Alright, so if you need to take a break, take a break. I hope you've been making notes as you go. They'll be very useful now. Come back and have a go at these. I would definitely expect you to be able to do up to here. And I would stop the video now and check the answers when you finish trying them all. Okay? Alright, have fun. Alright, so I'm going to add the units on the answers now. Here they go. Okay, so here we have the answers. I'm not too worried about significant figures yet. All I've done is I've ensured that I haven't given more significant figures than is available with the actual answer. So I haven't changed the number of decimal places. Anyway, we'll talk about significant figures next week in the lesson. For now, I just want to know that your computation is okay. I'm a bit worried about this one because I don't get the answer. The answer in the book is 5, and I'm always a little bit weary of not getting what's in the book, even though the book does make mistakes. So don't worry, if you get a 5, we can talk about this on Monday. Yes, have a go. Hopefully you can do all of these, and if you can't, you need to have another go at watching the video, I'm afraid. Anyway, see you Monday.